Okay, the beginning is planned like this kind of lecture on neural networks, so we may skip this and go to live coding, but this is your choice, so which would you prefer? Or maybe like this. Do you know how neural networks work? I see mainly no. Okay, so maybe for these people I will do the lecture, and if it will be too boring, then we will skip just to live coding. And if something is not clear, then please ask a question or anything. So it will be better if it will be more interactive. So okay, so I prepared to talk about neural networks as category, which is quite interesting. So we'll try to define a category of neural networks and use this definition to create implementation of them in Haskell. So it would be good to have some, at least, basic knowledge of how do they work, because we will be implementing them, so it will be nice. So what is our motivation for neural networks? Let's say we have some data set, some set of pair of inputs and desired outputs, and we would like to somehow model this relation between input and output, and interpolate it and extrapolate it on a whole space of possible inputs. So this is the main motivation of neural networks, and this is the main thing that we'll be talking about. So what is a neuron, at least in neural networks? So this is just a composition of linear functional with activation function, which seems like, okay, what this guy is talking about. So linear functional, at least for us, it's just a dot product of input vector with some kind of vector. The other vector is our vector that defines how the functional. And this activation function is any differentiable function on scalar value. So, for example, if we have, because we are interested in neurons, this is our main source of inspiration, then the main function which is used is looking like that. This is just sigmoid function. It's okay, what we want is to be able to differentiate it. And why is that? And how this will help us is such thing to model the relation between input and output. So this is graphically how it looks. We have our input vector, we have our weights. This is just a dot product of these two vectors, and we use activation function on the output. We also use bias, because linear functionals for zero vectors always return zero, and we don't want this. We want to be able to have any value at zero, which is desired. So we add some kind of bias. In practice, we just concatenate the input vector with, we append 1 to the input vector, and we just use dot product of this longer vector. So how does it work? Why do we do it like this? If we compose this with some kind of distance function, this is called loss in the machine learning terminology, which specifies how different the output from our network is from the desired output. Measuring the distance and computing derivatives with respect to our parameters, our vector, which is in our model lets us minimize this, because if we have our parametric space, so for example, let's say we have some kind of input. This is our parameter, and this is the distance. Let's say we have this parameter. So we compute the derivative here, and it says us where the distance will be smaller. So if we have this kind of tangent to this curve, we just go in the opposite direction, which is the direction at which it is lower. So this is, I think, kind of a neat idea that lets us help adjust our parameters so that we have the mean distance between our output and desired output minimized. Okay, so what is a layer? Because for now we have functional which returns scalar value, but we would like to be able to return something more. For example, we may have some vector of probabilities of which class does something belong to. So for our example that we'll be using, this will be every coordinate of our output vector will be number and probability what number is on the image. This is our case study. So in practice, this is, in theory, this is just stacking the neurons one over the other, but to make it more computably feasible, we just change the linear functional to transformation. So instead of dot product, we use matrix vector multiplication, which is just we take row vectors of matrix and get dot products. So it's basically the same. And in this case, activation function is quite the same, but instead of having the activation for whole output, we have a scalar differentiable function which we map on the whole output. So it's just something we'll like. This is how it conceptually works. So we have few neurons, they get the same input, but they have other outputs, at least desired. So the question we like to ask is, does it compose? So, and the answer is yes. If we have one neural network which returns us some vector, and we have another that can take a vector of this length as input, we can compose these two layers, and there's no problem with this. Because there is chain rule for differentiation, we can compute derivatives for parameters of the first neural network and the second one. So we always are able to do this. And as we are able to compose our neural networks, and we have this kind of objects, yes, these vector spaces that neural networks map one to another, then we can define a category. So we can suppose a set of objects our vector spaces, and as morphism we may take the neural networks. Because there is no problem with composing differentiable function, because the differentiation is closed under composition, we see that this is possible, and we may define category. Defining identities is, I think, trivial, because having identity function and identity matrix in our layer is something that I think all of us can think. And I think if you add something like this, then it does not change anything. So does that category has something else that's interesting for us? So what we can find there? So the main thing that you can begin with is the Cartesian product that is defined, because as Rn is a vector space it's in itself a Cartesian product of n copies of real numbers, and we can always disassemble this Cartesian product and assemble it again with having higher dimension. So this is something that we might use, and it might become useful later. So even if there is Cartesian product, there is, at least I can think of any it does not form a monoid because there is no unit for this in the vector spaces. At least I can't see anyone. If we take R to 0 maybe, but how is this defined? Okay, so if you have this Cartesian product, is this all? Of course not, because if we already are mapping scalar function over vectors and we say it's differentiable, so why can't we just map our neural network over this list of inputs and say that it's differentiable too, so why can't we do that? And yes, we can do that. We can do it with the same rule. And it seems that it should be working. Okay, so looking at faces, any questions?
The list of input vectors is a training set?
No, it don't have to be. It may be one training example. So yay, we have list functor. We have defined list functor in our category, because as we can create lists of vectors, and from our neural network we can create a neural network that works on the lists. So yay, that's great for us. So what can we do else with this? Because can we escape this list? Can we return to our beginning state? So what's the first thing that comes to mind when you want to come from list to one representative? Just fold. Yeah. So we can define fold, and will it be differentiable? This is the main question for us. Will we be able to pass our gradient for us? So if we have like this set of inputs, and you want to fold it, so we need an accumulator, let's say. So let's say this is our egg, and this is our neural network. So we take pairs, so as we said, this is closed under Cartesian product. So why cannot, if you have this with two inputs, then in general we can compute derivative. We compute this, our distance. We get derivative with respect to this, but we can compute it with respect to this, to this, to this. We can go everywhere. So it's closed under computation of derivatives, which means that it's well defined, for us at least. So it works. Yay, great. So after this, we should be able to start working on coding. Or at least, do you feel ready? Or want something more explained? Or we just will be hoping that it will come out while coding this? Okay.
Why do we model networks as category?
Because it will help us. We have defined these types of morphism that we can that we have there, and they are closed under this differentiation, so we can always generate them. So when we will be implementing this, we'll be using this. We'll be generating this GADT, which will represent all the types of morphism which we have, and we'll have evaluator for this.
Okay.
But first thing that there is thing that everyone loves. So how many tutorial on length indexed vectors have you read?
You mean the vector library?
No, I mean the length indexed on type level. So you keep the length of vector on type level, yes?
We saw one yesterday. We saw one yesterday.
Oh, that's great. Because this is the basis of our implementation of these vector spaces. But I guess this will be, this isn't quite complicated. Okay, so let's get to code. Okay, so I will set it up so I will see what I'm doing. Okay, is this color scheme okay?
The little highlight doesn't look so great.
Okay.
And maybe you can make the font black.
And what about this one? Okay, this is not good.
Dark background is way better for this projector.
Okay, so this one.
And it will be better on the recording.
So what would you think about this one?
Yeah, this is good.
Okay, it's great because it's my favorite. Okay, so before we start, or maybe because I created a repository for this on my GitHub, but you can do it on the fly if you want. We will be using some libraries, but I will be specify which ones. So, do you want this way, or you want see the GitHub one? It's just a stack project, the default one, so it just have this dependencies set. So
Let's do it this way.
you will just fly, yes? Okay. So the first thing we'll be doing is these indexed vectors and matrices. So it's called default because I don't want to be bothered. Okay. Because at the beginning I will be using the H-matrix library. So So we just it this way, and what will be needed is this quite readable at the top of the screen?
You want column vector plot? Like double down?
Okay, these are things that we can live without. And also okay, I think this is it for now. The all things that will be needed, we will be doing creating smart constructors. So okay, so I think type applications will be needed. And this is my favorite one. Okay. And the default. Okay, let's make this qualified. Okay, so to create smart constructor for our vector, first, because integers is the ones we would like to use the most, so we will create this not twinned function. Okay, the dot goes there. Basic syntax. Okay, it was something like. Okay, I have my cheat sheet here. So I guess we have to use data proxy. Okay, so what does this do? I guess everyone knows. We just get the type level natural number and create value level natural number.
In the new type, does the right vector need to be vs dot vector?
It does not be, because it's reimported by the linear algebra.
But you have vector. I mean.
The vs vectors are also in linear algebra package, and they are exported from there. So we can.
You have new type vector, and on the right hand side you also have a vector, and there is no conflict.
Okay, thanks. Yes, that's right. It is a conflict. Thanks. So we'll hide the vector from here. Thanks.
Also, instead of equality, do you need double question, double?
Yes, of course. Basic syntax.
What is proxy?
Proxy. Okay, so this is this kind of cheats that we are using. It is the singleton for every type. So it serves us to, because in general we cannot write functions that just take type as our value. So we cheated. The nutval takes proxy, which in type has a proxy and the reified natural number. This converts us. This converts this to some kind of integral, and from integral I want only int. So let's see. Okay, data kinds, of course. Okay, I forgot what is wrong there. Maybe this will be easier.
So one thing I haven't seen is the at operator. What is it doing?
Which one? This?
Yeah.
This is type application operator. So on the right-hand side, this n is bound here as a type variable. And because of scoped type variables, we may use it in the body of the function.
Okay, so it's basically a proxy of type n.
Yes.
Don't you usually not write a space after at?
I'm sorry?
The codex before it doesn't have a space. Usually they avoid putting a space between at and
Okay.
yeah.
But there's some.
Yeah,
Yeah,
it's the same thing. As well.
Okay, so I have this. What kind of problem? Okay, so some problem with modules, and this is why it's not compiling.
You should move the module declaration up above the import settings.
Okay, thanks. So I'm lost in this Windows.
The beauty of it's not.
Yes, it's great, but sometimes it just.
What library do you need for the linear algebra?
H matrix.
And vector for the data vector?
Data vector, yes, just the vector library.
Yeah, the library's got vector.
Yes. Okay, so how does it display? Still could not find. Okay, I haven't wrote the where. Oh, okay. Xmonad, I love you, but don't do this to me. Okay, so cannot deduce. Okay, now I'm quite. Because we have this for all n now not n. So are we this?
If you use XC type application,
I'm sorry? Yes, I have type applications and scoped type variables. I think I may need. Okay, this is not it.
so you can either enable the extension allow ambiguous Or you can change the type of nut to int to take an end.
So you mean that I should just do not, or?
You can either enable allow ambiguity. The problem is that if you type nut to int,
Uh-huh.
it will be ambiguous and it won't be clear what integer to apply. So you can say you can enable language option allow ambiguous types. That's in the error message.
Okay. Okay, it's great. Okay, so with this we can create our vectors from lists. So we have these constructors, let's say okay, let's make it more explicit. Yes, because we will need it. Okay. So to make sure that the list is not too short, we may always cycle it. Then take the amount of numbers that we want. So we take and construct a vector from this and get it in our constructor. Okay, let's see what. Okay, he does not allow this because I don't have kind signatures. And now it's great. Okay, so what we would use is just for debugging purposes. It seems to be working. Okay, so everything's clear for now, at least.
No nut is defined in typelets, right?
Yes, the noun nut is in typelets and the whole nut kind. At least this one. Okay, so sometimes we don't want just to pass these lengths explicitly, so we will just use this. this will save us some for all, so we don't have to bind these ends into the scope. Seems to be working. Okay, so for now we can do the same for matrices. So maybe just to hide it here and have it as qualified import. So you want to see it? Okay. So the main difference is that we will use two nuts for matrices. And also a smart constructor, but first we need to replicate our work on vectors. So okay. Okay, so I have this convention, so I will try to keep it. Okay, so it looks that he does need it in the for all. It's okay, we don't mind, at least for now. So with this we can construct matrices. Okay, so this would just be and thankfully the linear algebra package exports this nice constructor that we will use. So this is just oh, okay. So we don't have our matrix, so we cannot. So we will need it. and just wrap it in the matrix constructor. So what's the problem now? Typo, okay. And this is something that's always nice to have. Well, it looks okay, I guess. But what will be most interesting for us is to have this matrices with random variables, because at the beginning of when we create neural networks, we want to have random parameters because we have completely no idea what they should be. So another import. It's where was, I think it's like this.
Why do we need n and m in new type matrix definition?
Where?
I mean, you have the new type, and you have n and m. Could it be just
I think it can't be. It just derives this as type and not as something of other kind.
But those two type variables are not used anymore.
Yes, but that's how it derives. This is I think how the type checker works.
You mean that it doesn't show up in the right hand side?
Yes,
It
because
kind of carries.
It defaults to
it defaults to a type.
unless you have polylines, then it will be polymorphic.
But then it would be polymorphic, and we would just nuts, not anything. Okay, maybe I'll just copy it. Okay, our biggest friend IO. So we will need the same hack here. Or do we? Yes, we need. So we can just use mat from a list, but we need this product. Okay. This will be like this. Okay. So we'll take this small interval as our place, and of course we need, I guess, control monad, or Okay, so does everyone catch this up? Oh, it's too quick, too slow? I guess too slow is the more probable answer, but
I think it's fine.
okay. So I was reminded that there should be break in 2 minutes, so maybe we should stop at least now, because this is this preface of our matrices and vectors, and then we will start creating our GADT for neural networks after the break. And for motivation, may I change the picture? Will be fine? Or
Could you keep it open?
oh, sorry?
Could you please keep it open?
Okay. So these are our extensions. For now, at least. And our imports, so maybe I'll make this. Okay, so this made it smaller. So for now, the libraries are vector and H matrix. And for now. So if you have any problem, just ask. Okay, so I think we can take a small break for now, and if anybody has questions, then be welcome to come. Okay, so let's get this running. Okay. Now that we have our matrices, we can start to try to define what our networks will be. So the basic thing we said about neural networks are these layers, because when you have matrix of width 1, it's just the same as neurons, so we will only define layers. So okay, let's start with data. Or maybe this way. So what we need our matrix. So we will have we need it, or do we not? I'm not sure. I think we need, but so the basic thing is we want to append to the vector this one value, so we have this our bias, so we will just use this. So maybe let's format it a little. The next thing we need is our function. Okay, so we need another extension. And we want this function to be differentiable, and we have this AD library I mean, we'll have in a moment, which needs as input polymorphic function for numerals. So we need and this gives us type operators, okay. And of course, as we use it, and redundant bracket.
So what extensions did we enable?
Okay, so we added type operators and Rankin types.
And what is this AD library?
I'm sorry? It's just called, I think, yes.
Called?
It's just called AD. We are not using it, but we'll use it because it's quite neat that we don't need to compute derivatives by ourselves. Okay, so having this, we may now try to think about how to pass our input through the network. We have only this one. We'll be adding more variants as the composition, etc. later. But now let's get to the point where we will have this one layer that we will be able to train. So let's say that we have some kind of conducting signal. Just to be sure I write it. So we want the vector to be first, or maybe no, we'll just take. I think this more. So this is quite obvious. We just have our vector of length n, which is our input in the network, and we output the vector of length m. And in our layer we have this thing as matrix and function.
You have to switch the order of the arguments.
Yes.
So if is the activation function, right?
I'm sorry?
If is the activation function. If it's the activation function.
Division? I'm sorry?
Czy f jest funkcją aktywacyjną?
Okay, f is activation function, yes. So this is the second argument here, so it looks like it's this way, but if you want to do this, we need to have some way of mapping the function on the vector, so we just have this. We could do this with lenses, but I don't know which way is preferred, so I will do this way. So we know that vector map will not change the length of our vector. So okay, he seems to not be worried. And the second thing we need is our vector matrix multiplication, or matrix vector. Okay, so my convention was the other way around, so let's stick to it. Well, it's just straightforward. We just take this. Okay, I see I use the abbreviations too much. It needs, yes. Okay, now it will be fine. So this one is the matrix vector operator from the H-matrix library. So we'll just use this. So we don't need to implement it ourselves. And one thing that's always liked, so we'll make our cons. So this time we will need because, as I said, we will need to cons just one at the beginning of the input vector, so that for 0 vectors we don't get zeros but some other value. And after this it's just straightforward, because we have, maybe we don't need this because we need, but it will be great if I would put some definition here. So this should type check now, and it doesn't. Okay, that's great. Okay, maybe not this way, but this way. Okay, you're rewriting this? I guess. what we'll also need is this constructor for random random layers, which we might add here. Of course, the function must be supplied because that's not something we don't want defaults here. And this will just be so we will have our conventions, they change all the time. As does my if I remember correctly, this will not work. But this should. And we need it as an argument, so. I guess this will need a non-nut solver at this moment. So how was it? I have my cheat sheet here, but it's, I guess, too big. So it will be, okay, it's in the different pragma. And there should be this.
Can you show that again?
Okay, here you have top. Well, it's suggested this way.
So what does this extension do?
Okay, so this is not an extension, this is the plugin of the type checker that solves these equations, because we defined in our constructor that if you have layer and that layer will have input of size n, the matrix should have n+1 width.
It says could not reduce.
I'm sorry?
The compiler says could not reduce.
Yes. It couldn't reduce this, but with this plugin it can, but it must be, I guess it's in the Cabal.
How do you install this?
Sorry?
How do you install this?
So in the Cabal you just need this to the dependencies.
Yeah, the package is called GHC-net.
Yes, as
You can just add it as a dependency and then Cabal should install it.
add some import?
I'm sorry?
Should I add some import?
No, you don't need. Just this language, just this options pragma. So if everyone has it. Okay, so we might check if it's working. Okay, I've done some terrible things. This is not I/O. Yay, great, something is off. This is exactly this thing that we wanted to avoid. So I guess what is wrong is that it stores the matrices in the row major format. So if you want this to be input, okay, then this should be the input and this should be the output for a matrix, and it means that with the matrix vector multiplication we or maybe not. We will keep to this convention, but change it here.
So what changes did we make?
For now, let's check if it works. Yeah, it works. So in the constructor of matrix, the list constructor, we just need to swap the height and width in this operator.
That's it.
That's all. Okay, so we have this quite few fun things. So let's see if we will be able to train this thing. So what we want is to compute the gradient for the matrix which we have and modify this matrix with respect to this gradient with some constant. So let's call this. So let's do it in small steps. Let's have something like this. We have this training example, so we will just so for as input, let's have our function, this loss function of, we just need its gradient, so it does not matter. So maybe we'll this time start with definition and then we'll take the type. So we have this function, we have our network, so at this time it will be layer. So let's call it properly. And we have our example, which will be per maybe not output, but expected. So we will need our so we need to have some trained layer, which is trained on this example. So this will be layer with the same activation, but it will have, well, to be more explicit, okay, still typo. So we need these new weights. This will be old weights minus something called training rate, which is the speed with which we will go down the slope. And this will be times okay, so this will need another thing which we'll need. This is, or maybe just and we will have float on the beginning. So we want to be able to scale our matrix with some value so we don't overshoot our minimum. So let's go this way. Okay, we don't need this. This will be just, so again, this library gives us, I'm not sure if it's called this way. So this is just a function from the library that scales it for us underneath. Okay, so now we need to compute this. So the first thing is to get our output so that we know how much we overshooted, we made a mistake. So and we need this input. Okay, and I need to check the cheat sheet for the derivative. Which I have somewhere here. Okay, So this derivation is not so complicated, but to remember it's someone must be a cyborg. So when we have our output, we just need to compute this gradient. We have this loss gradient, so we compute loss gradient to get gradient from output and now okay, because we will need vector transposition. So again, to keep it safe but still simple, okay, this will be this weight gradient that I so gladly was talking about. Okay, everyone's here? Okay. So this will be our, we take our inputs, matrix vector multiplication okay, with some, I'm not sure if I've got this right, but yes, it is right. So we are consing 1 to this vector, multiplying with our weights. This is.
Did you mean input?
I'm sorry?
Did you mean input?
Yes. And there should be dollar here. Okay, I see. I've made my differentiation cheat sheet a little too simple. So it's this. Now we will need derivative of our activation function. So we have so this is differentiation from the AD library. It works because this function is polymorphic, with only constraint being the num constraint. So we map this, but we need, yes, okay. Or maybe just And now with this, so this was a little that we still need to take outer product. So this is the another thing that I forgot to do here. So this will be
vector.
I'm sorry?
That has to be vector, right? The constructor.
Vector, yes, constructor. Okay, and we'll compute outer product of, so we would, it would be cool if we had a vector-vector multiplication. Okay, so it just needs one of these.
What is the vector-vector multiplication?
It's just point-wise multiplication, so according to coordinates. Okay, or no? Okay, there's something. We have two arguments here.
Also, shouldn't there be a dot after the VB1?
Sorry?
Shouldn't there be a dot after the first line of weight gradient?
Where exactly?
You're missing
A dot, okay. Okay, so can't match type matrix with vector.
Also, loss gradient is not defined.
Loss gradient is our parameter. Okay, we want, so let's say that we have to get better errors, we just write a type for this. Or as I'm using this as output. Okay, so what will he say now? Okay, he still sees a matrix here somewhere. And to where does he see it? Okay, so I'm quite stuck here, so let's add more types. So we will need this for all. Yeah, does not matter here. Okay, so he wanted it at the output, and this will be only when we will get this outer product. So we will need outer product of this with our input with cons 1, and let's see if we have this in the proper order, because it seems to be off. So we need to change the order on the outer product, and then it will, or it should, okay, I'm sorry, I'm making some commotion which is not needed. It was in good place, so we will see at least. So outer product with and of course a typo. Okay, and now to create the string of all.
You mean your dot?
Yes. And we don't have a num instance, so we may define num instance or just do it like this. So this will be okay, I write it the other way all the time, so Okay, so everyone got it? Because it seems to be not okay. Because I am lacking one matrix here. Okay, so now dollar and yay, it type checks. Wow. So let's take the same example. Let's see if this works. Okay, so let's take this as an identity, but we want to have some kind of operation of our vectors, so let's use multiplication as our gradient. We don't care too much, at least for now. So it will be vector multiplication. Okay, it seems to be working.
Could you explain what we are calculating here?
I'm sorry?
Could you please explain what we are calculating here?
Okay, so at this point, we want to calculate the gradient with respect to our weights. So we want to have our neural network, which is the composition of these two things, this multiplication by matrix and activation function. And we want to have derivative with the respect to the weight. So we have our weights, we have our loss function, and we have our weights. But loss function is a composition of our neural network and the loss function in itself. So from the chain rule, we get this this will be output, and derivative of output with respect to weights. So now this is our output gradient, because we pass not the loss function itself, but this derivative.
So the loss gradient that is being passed, what is that?
I'm sorry?
What is the loss gradient argument?
It's as the argument.
Yeah, so what is this argument?
So when we have our loss, which is our our distance between expected output and the one that we made, we may generate this gradient of this as a function. So we compute the gradient function of this loss, and we use it here at our output. Then when we have here, we can expand it from the chain rule. So we have our output with respect to activated, I mean before activation, so we have activation with respect to weights. But the activation gets the multiplication, so we get this. These are all the steps. So this is the activation derivative. Is here. with respect to the output of the multiplication. And this outer product is the derivative of the matrix vector multiplication. So we have all this in this composition. But we want to compute this for our input. That's why our input is applied here. So this is something like this. I'm not sure if there will be enough time for now to get, because okay, so this is also why I wanted to use the repository, because I have downloaded the MNIST dataset, but I guess we will have to finish soon. So, so in 2 minutes I don't think we'll be able to write this, but what we want to do is this here. Okay, so the search for the right window, which I guess will not exactly end well, but it's okay, as I have my cheat sheet. So what we want to do is something like this. We have these numbers, and we will predict what number on the image is there. So we're really close. We will only need to parse it. I think I will just throw some parser to download for the next lecture or this workshop, at least. So tomorrow we'll be having fun with this. And we'll be implementing, adding more layers and recurrent networks. So maybe some text corpus will be there. So this is what this will do when it will be ready. So it seems like just a bunch of random stuff, but at the end, this is what it does.
You're going to implement backpropagation tomorrow?
Yes, we will implement, because we now have the computation of the gradient for one layer,
Exactly.
and we will just generalize it for the... But this will be on the next lecture, yes? Okay, so I think we will end for now. Any more questions? Okay.
Will you give us the link of the repository?
Yes, of course. So it's I will push there what I have for now. It's this. There are some redundant dependencies in the Cabal which I think we will not use, because I thought it would be faster. But still, nonetheless, I will push the existing code there, and so okay. Okay, so for now, maybe we'll finish.